Thank you for the introduction and thank you for having me here and giving me this opportunity to give a talk here. So today, as the car introduced, today I'm going to talk about the topological normal generation of the Big mapping class group. So let me first define what is the mapping class group first. So probably everyone already have well known the definition, but let me just recall it again. So mapping class group is if you have a oriented surface, so this one is a two-dimensional surface which is oriented, and possibly with boundary. So the mapping class group of S denoted by map S. So the reason why I didn't use mod S or MCG of S something, but is because for the finite case, it is actually I actually same with the modular group, but if you go to the infinite type surface, then it is usually not. So that's why I just use this notation. So anyway, so denoted by map S, and this is defined to be the group of isotopy classes of orientation preserving homeomorphisms of S that preserve the boundary pointwise. So you fix the boundary, and then you can do anything, which is a homeomorphism inside of the surface. So you can write it like this way. So as you can see, you can write it like this way. So here, this plus means the orientation preserving, and homeo zero is the group of the homeomorphism, which is isotopic to identity. So this means you just cut out with the isotopy and then consider its equivalence classes. So there is a type of surface. So if you have a surface which has only finitely many punctures or finitely many genus, then you say it is finite type, and that is equivalent to that the fundamental group is finitely generated. So otherwise, if the fundamental group of the surface is not finitely generated, then it is called infinite type. And as I just said, equivalently, if you have either infinitely many punctures or infinitely many genus or both, then that surface is called infinite type surface. Okay, so these are the examples of infinite type surfaces. So as you can see, the topmost one, which has infinitely many genus, which strives to the right, and this surface is homomorphic to the cartoon on the left, on the right one. So you can see there is a lake, and then over the water, its back comes it out and in and out and in and out and in, and those will make a genus, and if infinitely many genus. And this looks like a Loch Ness monster. So that's why this surface is called the Loch Ness monster surface. Okay. So, and such genus might accumulate in the various way, like you can see in this case, the genus dried out in a three different way, and then it escapes to any small compact region in a three different way. So there isn't a nice name, but yeah, you can consider this kind of a surface as another example of the infinite type surface. And then you can also consider the punctures. So usually in my drawing, every such kind of a thing, like a cusp, will denote the puncture. So we have infinitely many punctures, which goes to the right and also goes to the left, and then infinitely many genus, which goes to the right and which goes to the left. So this kind of a surface can be another example of the infinite type surface. And yeah, and this punctures or genus can accumulate in a various way, not a finite way, but it can accumulate like a counter set on the as you can see in the example. So every genus just duplicate itself and again and again and again, then it'll accumulate in the counter set way. So and more complicated things might happen. So these are just a very, very small slice of the examples of infinite type surface, and you can draw it anyway if it is guaranteed that you have infinitely many genus or infinitely many punctures or both. Okay, so let me just see what is the what different thing happens between finite type and infinite type. So if you have a finite type surface, and classically the mapping class group of the finite type surface S is discrete. So this means when you have a homeomorphism group and then cut by the homeo zero, then everything became just this discrete. So yeah, so if you want to consider this one as a topological group, then this is just a discrete space and every point is isolated. But however, infinite type surface, we can also give the topology on the infinite type surface with the compact open topology on the homeomorphism groups, the orientation preserving homeomorphism group, and then cut it out again. Then in this case, identity is not anymore isolated because you can consider that you choose the exhaustion of the surface, and then exhaustion means you collect the compact set which is bigger than the formal one, and then you go bigger and bigger and bigger, and then consider the any map which is identity on that compact region, and then if you just push out something which is not identity, push out the region which is not an identity, and then it will converge to identity. So this gives a converging sequence to the identity. So that means with this topology, this is infinite type Bing mapping class group. So the mapping class group of the infinite type surface is non-discrete, and then but still it is Polish group. Coming back to the finite type surface, the mapping class group is finitely presented, and there are many generators and many presentations, and maybe everyone already will understand about this one. But in the infinite type surface, it is uncountably generated by its nature and not even compactly generated. So it means because we are dealing with the topological group, we can consider the generating set and its topology. And for any complex set in this infinite type surface, it cannot generate the whole group. So that's the meaning of the not compactly generated. And there is a nice theorem, nice aspect on the finite type surface. Like if you have a genus larger or equal to 3, then it is perfect. So it means mapping class group itself is identical with its commutative subgroup. But George Domat proved that the big pure mapping class group is never perfect. So here, pure means every map you collect the subgroup of the mapping class group, which you collect all the punctures or all the ends are fixed. So in this case, it is never perfect. So let's go with the normal generating aspects. So that's what I want to say today. So let's see what happens on the finite type surface. And fortunately, Lanier and Margalit already proved that with the same condition as we saw in the perfect thing. The mapping class group is normally generated by pseudo-Anosov, whose stretch factor is smaller or equal to the square root of 2, and any periodic mapping class group which is not hyperelliptic involution. So there are many normal generator of mapping class groups. So normal generator means if a group is normally generated, it means you have elements and its normal closure is itself. Not itself, sorry. Its normal closure is the whole group. And here, H back, Pyongyar back, who is we're sharing with my last name, but we're not relevant relatives. But anyway, he's my advisor, and him and Dong-Yeol Kim and Chen Si-woo also prove that there are also many reducible elements which normally generates mapping class group. Yeah. So coming back to the infinite type surface, Lanier and Vlamis prove that mapping class group has a dense conjugacy class if and only if it is uniquely self-similar. So I didn't say anything about the uniquely self-similar, but we'll see in the near future. And then Caligari and Chen also prove that for any finite surface and then consider the contour set embedded, and then you just delete those contour sets, then it is normally generated by an element F if this F tilde normally generate the map S. So here F tilde is, you forget all the contour set part, and then it'll give a nice isotopic class in the mapping class, nice isotopic class in the mapping class group of this finite type surface S, the ambient surface. So if this F tilde is a normal generator, then it will give a normal generator of the infinite type surface. And also Vlamis and independently Malestin and Tao, they prove that if S is self-similar or telescoping, then mapping class group is normally generated by just a single element or some nice involution. So somewhat analogous from the Lanier Margalit theorem, like if you can find a nice periodic elements, then you can generate the whole group, normally generate the whole group. Okay, so those are the difference between the finite type and infinite type. And then let me just point it out why I'm carrying the topological normal generation. So the group G is normally generated by F if the normal closure is G. And topological normal generation is you just add every property with a topological thing. So we are considering the topological group, and then it is topologically normally generated by F if the normal closure and then taking the closure, in this case, the topological closure is dense and then it is itself G. So it means if the normal closure of F is dense, then it is called the topological normal generator. So by its definition, if G is normally generated, then it is, of course, it is topologically normally generated. But the converse does not hold in general. So Domad and Dingman also proved that there is a surjection from the mapping class curve of the Loch Ness monster surface to the Q, the rational number. So therefore, it is not normally generated, right? So because if it is normally generated, then when you send it to the abelian group, then it must be cyclic, right? So because Q is not cyclic abelian group, so it is not normally generated. But Loch Ness monster is in fact a uniquely self-similar surface, one of the uniquely self-similar surface. So just invoking the Lanier theorem, it is topologically normally generated. So there is a nice so the normally generated condition is a little bit more strict. Okay, so let me now explain what happens on what is the nice, I mean, some aspects of the some features of the infinite type surface. So here, one thing is the end. So end is equivalence class of the sequence of the subsurfaces. So here, if you have let me say, if you want to find this end, then it is defined by you cut it out here and then cut it out here and cut it out here. But actually, anyway, but it shrinks, and then the whole intersection should be empty. And then there are many such kind of a sequence, and there is an equivalence class, and that equivalence class is defined by if you have two sequence U and V, and if you have some big enough for any integer m, and there exists some nice integer n such that Vn is always considered contained in Um. So it means this means we only care about how they shrink and where they converge. So punctures are also the ends, and then if your such sequence always contain the genus, then it is called the genus ends accumulated by genus. So we say we collect all the ends, and it is said E to the S, and here EGS is we collect all the set of ends accumulated by genus. So if I see what is the end space of this one is you have ends punctures which accumulates both two, and then there are another ends which accumulated by genus on to the bottom way and then go to the left way. So here these points are also the set of the ends which is accumulated by genus. Caragiotto and Richards prove that those two will give will completely characterize the infinite type surface. So if you have any infinite type surface, then the set of ends, the end space, and then end space which is accumulated by genus, and those two will give a complete characterization. And those two are just nested closed subset of the contour set. So as I just pointed out, the mapping class group of infinite type surface is not even completely generated, so it is hard to understand its coarse geometry. So thanks to Rosendahl, he proposed the coarse boundedness. So if you have a Polish group, actually this is not just the topological group, but it has to be, I think, a Polish group. But if G is a Polish group, and then say A is a subset of G, and then this A is called coarsely bounded, abbreviated CB, if every compatible left invariant metric on G gives a finite diameter. So it means in a coarse way, you can kind of ignore this small set and then consider it as a point. So if you have CB generated, at least CB generated one, CB generated topological group, then you can define its coarse geometry, its large scale geometry. So here, if G is CB, if G itself is coarsely bounded, and if G is CB generated, and if it admits a CB generating set, and if a group G is locally CB, if there exists a CB neighborhood of an identity. So there is a inclusion relation. So CB implies CB generated, and CB generated implies locally CB. Okay, so this is my main question. So when is the big mapping class group topologically normally generated? So we already know that there are some kind of some nice sort of infinite type surfaces with whose mapping class group is normally generated by a single elements or involution something, but we do not know if we just if we just consider a more bigger class of the infinite type surface. So that's my question. And then second, if it were not topologically normally generated by a single element, then how many do we need? So as I just pointed out, usually infinite type surface is not infinite type surface. The mapping class group is not even not countably generated. So we need a set, but it cannot be a compact. But when it comes to the normal generation, what can we say? So those two are my question, and my upcoming paper answers those two in a little bit restricted way. So here we suppose that our infinite type surface is tame, and then if it has a countable end space, and then its mapping class group is CB generated. Then this S is uniquely self-similar if and only if it is topologically normally generated. So let's recall the Lanier and Vlamis theorem. So they said if surface is uniquely self-similar if and only if it contains a dense conjugacy class. So if it has a dense conjugacy class, then just taking the closure, it'll give a whole group. So if it is uniquely self-similar, then it is topologically normally generated. So the converse way is my work. And then the second answer to the second question is the upper bound of the minimal number of normal generator. So here, again, same assumption as this tame infinite type surface with CB generated mapping class group, but in this case, I didn't restrict to the countable end space. And let M be the number of distinct type of maximal ends in S, and then C is defined as follows. So here C is something like this one. So here A and B are distinct maximal ends, and then this one is some ends type which accumulates to both A and B. And then considering all the types of those C's, then those M and C are only depends on the topology of the surface, and then it is topologically normally, and then the mapping class group is topologically normally generated by M times M plus C minus 1. So it is bounded, and then since M and C depends only on the topology of the surface, so M plus C square will bound this one. So this means it'll the minimal number of normal generator is bounded quadratically with its topology. So that's the theorems. And then I think it is almost 20 minutes past, so I think I should give a idea of proofs for the first one. So the main obstruction to prove that one is this one. So if you have a topological group G and a H be a non-stickily abelian group, and then if there is a continuous surjective homomorphism from G to H, then it cannot be topologically normally generated. So this one is easy because if it is topologically normally generated, then we have a continuous surjective homomorphism. So every conjugacy class and then its closure will goes to the every conjugacy class and its closure goes to one element, right? One element and its power. So it has to be cyclic. But if we have a non-cyclic abelian group on its image, then it cannot be. So this one is just the easy obstruction. And then the hardest thing is to construct this homomorphisms. So let me just introduce the first idea of proof. This one is Man-Raffe's small zoom condition. So actually they proved a very, very nice locally CB criterion. So they completely gave a criterion on the topology of the infinite type surface, which infinite type surface admits a locally CB mapping class group. So these are really, really big, but the essence is this one. The essence is the small zoom condition. So technically they said there is a nice surface decomposition, which cut out one big in the center, which looks like a sphere deleted with a lot of disjoint disks. And then all of the other things are attached, and those attached things are uniquely self-similar or perfectly self-similar. So self-similar surface, which I didn't say anything. And the small zoom condition is more crucial. And small zoom condition means if you choose any ends like here, any ends which not like this punctures, but any ends which goes out like this way, then you can always find a small neighborhood. And if you choose any small neighborhood and there exists this homomorphism FB such that this contains the end set. So it means you can push. So like if you have this point here, and then you can push. So here, for example, if the surface doesn't have this kind of a genus, then you can, if you cut like this way, then those two genus is an invariant of the complement, right? Because you cannot under a homeomorphism, you cannot add the more genus or subtract some genus, and those two will be the invariant of the under this homomorphism. So it means if you have an end which was accumulated by genus, then there must be one more. And if you have this kind of a punctures, then there must be at least one more. So that is the small zoom condition. Okay, so the second second idea is the handle shift and the generalized shift. So handle shift is nothing but just push those genus to the right. So this curve goes to this curve. And then generalized shift is just nothing but just, again, another shifting. But in this case, not a handle, but something a little bit bigger. Okay. So this one goes to here, like this way. Okay. So if you have a generalized shift, then the one thing I want to point it out is you can count how many you shift. So here, if I send this one to here, then you have one. So here, if I send one handle to the right, then you shift by one. So this will give a surjective homomorphism to Z. And if I first consider every maximal ends are fixed, then if we have two independent those generalized shift, then those will give a surjection to the Z square. And those are continuous surjective map. So because of the obstruction, it cannot be topologically normally generated. Okay, so this one is the first one. Okay, let me just skip this one. And then to enlarge my result to the full mapping class group, we also have to consider the permutation on the maximal ends. So here, if I have those 2 points, if I only consider the fixed one, then this one and this one cannot be the same, right? Because those 3 points here and here and here are fixed, so I cannot resolve anything. But if I also allowed to be allowed to permute these pieces, then this one can be conjugate to this one by just permuting on this side by taking the half twists, or taking the half twist. Then you can just change the order of these pieces. Those two goes to those two, right? Okay, can I have 2 more minutes? Sorry, let me just finish it quickly.
Yeah, sure.
So
Go
in
ahead.
this case, okay, thank you. So in this case, we have those kind of a half twist, and those will give if you have a generalized shift like this way, then those will conjugate to this one. But one thing I have to point it out is that it still have a parity thing. So it means if you just send it odd number of this one, then odd or even, then odd and even still remains under conjugation of this half twist. So that's my second one. So if you care the parity and the sign, so here we permute the maximal end, so we can ignore everything and which permutation happens on the maximal ends, then we can see this sign, right? The odd permutation or the even permutation. So those two will obstruct the normal generation. So we have a continuous surjective map to this one, and this is a little bit, looks like a little bit complicated, but in essence, it measures the parity, and the last one will measure the sign. And those are also surjective homomorphism and continuous. So it is obstruction. Okay, I think, yeah, that's all today. Thank you for your attention. And if you have any question, please.
Thank you. So are there any questions for the speaker?
So I have a question. It seems like your proof also gives a lower bound on the number of minimal generator. Could you?
Oh, yeah, right. Yeah, in my upcoming paper, because you saw my draft, so you have that question. So the lower bound it depends on the just type of which different maximal type of the isolated maximal one, isolated maximal ends. So here, if you have this one and this one and this one, so those three are the different type of this surface, then you can see there is at least one shift, right? And again, you have at least one shift here. But in this case, you already have this shift and this shift, so nothing left, right? So if we write it like M-iso, so iso stands for isolated maximal ends, and then -1, because what you saw, what would you see, what happens in here, every generalized shifts are already exhausted by the other ones. So M-iso -1, number of shifts happens. Right? So those kind of a thing will give a lower bound, and it is also depends on the topology of this infinite type surface. And the other factor is this half twist things, and then again, yeah, it'll give something.
Thanks.
Yeah, that's really great question. Thank you.
Okay. I just have a quick question. So you mentioned that the infinite type surfaces, the big mapping class group is not perfect, right? This was some result.
Yeah.
Is it known what the abelianization is? Or like, can it have
Oh, yeah, that is really great question. In this case, not just the full big mapping class group, but its pure mapping class group is not perfect.
Sorry. Yeah, sure.
Yeah. So yeah, in this case, Doma also give just the structure of the infinite type surface, the abelianization, and that abelianization contains uncountably many rational numbers.
Okay.
I mean, rational number product is uncountably many. And then there might be a torsion, and there might be some kind of a proof for group things. But his question, which is still open, is that whether or not there is a torsion.
Okay, I see.
Yeah, so we do not know whether or not there is a torsion in the abelianization.
Okay, that's interesting. And what about the higher homology groups? Like, is it known if it's like at some point, or?
Yeah, at this moment, I'm not really sure, but there is a paper about calculating the higher homology, like H2 or H3. Yeah, maybe Caligari or Palma Wu with Yuigo Pallier, maybe. Yeah, they prove that the second homology group of some kind of an infinite type surface, which I forgot, is maybe Z or Z2, I think.
Okay, that's cool. So there's a question in the chat from Jinsuk.
Yeah, that's another really, really good question. The tameness, I didn't say anything about the tameness, but tameness is nothing but your surface is really great. behave really well and accumulates really well. And the tameness is important because unless the tameness, we cannot guarantee there exists the generalized shift. So if you don't have any tameness, we cannot guarantee there is a, if you have a, if you don't have a tameness, then there might be many maximal ends, but there might not have any generalized shift. So we cannot utilize this and construct this continuous surjective homomorphism. So that's why the tameness is needed.
Okay, I'll just say for the video, the question was, would you briefly explain why the tameness of a surface is needed? Just for the recording link. Okay, well,
sorry to interrupt.
let's thank the speaker again.